Not until we come back from spring break. Yeah. Physics 1 has a test next week, but this class doesn't have one until the week after, which is after we come back. Here you go. Why don't you sign in on that and start that around the room. What does ECD stand for? Ah, okay. All right, well, we got started on chapter 21 last time, the electromagnetic induction and Faraday's laws. And I would like very much, if possible, I would like to get through transformers today. Because next week, I want to start doing, we're going to get into actual inductors and putting some of this, all this inductance and such into use in electric circuits. And actually the first practical application in terms of electronics and electrical circuitry, motors, servos and motors and generators notwithstanding, is when you start using these phenomena to do transformers. So, last time we looked at induced EMF. Who can still tell me what EMF stands for? Electromotive force. And what are the units of electromotive force? Volts. Electromotive force and potential are the same thing. Now we looked at Faraday's law of induction and how the flux passing through a unit of area, it will induce an EMF as the flux changes, the change in flux per unit area, per change in unit time. We even did a couple of calculations and determined how much current would be induced if a coil of wire was rotated and changed, the amount of flux through the loop of the wire changed per unit time. And we also, in doing so, began to understand how the faster you move that loop of wire, the more current it's going to induce. Did everybody sign in? 1, 2, 3, 4, 5, 6, 7. Yep. 7 good. If anyone else comes in, help me remember to have them sign in too, please. All right. I guess that's a good place to pick up. Let's pick up on example 21.4 on page 595. Pulling a coil from a magnetic field. So we start with a coil of wire, like so. We'll let the book tell us how many loops there are. 100 loops, okay. Anyway, it's in a magnetic field. uniform magnetic field that drops immediately to zero at this line. Do not ask me how you make such a magnetic field. Okay, but in this fictional magnetic field, there's no fringing. Fringing not allowed. So. Now, N equals 100 loops. L equals 5 centimeters. And B sub naught is 0.600 Tesla. So the loop gets pulled out in this direction. Perpendicular to the field, magnetic field, and it takes 0.100 seconds for this for the whole thing to get pulled out. So the first thing they want us to determine is A, the rate of change of the flux through one loop of the coil the total EMF and current induced in the 100 loop coil how much energy is dissipated in the coil, and D, the total force required to do it. And that's the part that I really want. This is the reason I want to work this exercise. So get out make sure you pay attention here. When people start, especially electronics technicians, engineers, when they start working with all this stuff, it's all too easy to start thinking that this is just mathematics. You know, I think I've told you about the time I was building a laser in undergraduate school, and you know, the whole thing was powered by these little AA batteries. It was, you know, big fat hairy deal. Well, the multiplier circuit in this power supply was, because of the resonances involved and everything, it was cranking up that, you know, that 3 volts of AA batteries to like 15,000, 20,000 volts to fire off that laser tube. And the first time I accidentally touched it, it flat knocked me to the floor hard. It was it's easy to forget that all of this is not just fiction. It's not just imaginary numbers. I mean, mathematically it's described with imaginary numbers, but it's actually very real. You have a magneto. How many of you know what a magneto is? You ever gone fishing with a magneto? No? Take the wire. The magneto is like a magnet that you crank in a wire, and it produces, like, some people call them mega ohmers. It's for looking for weaknesses and for doing high potential testing, for looking for weak spots in the insulation where you can create an arc and break down weak spots. Well, you take that magneto, you toss the leads over the side of your boat into the water, and you give it a few good cranks and wait for the fish to float up. You can also get worms with it if you just want worms for fishing. You drive a couple of ground rods into the dirt, hook the magneto to them, sit there and crank on it. You'll drive worms right up out of the dirt. Point is, if you've never used one, you probably don't have an intuition for this, but when you start cranking that thing, it takes some effort to do it because you're actually generating you're expending some significant energy to generate all of that, to induce all of that EMF and all of that current. So that's why I want to work this problem, this example, to drive the point home that this may be unseen forces. This may be forces that act at a distance, but they are very real forces. And when you start trying to crank a generator, when you turn a generator, there's a reason it takes a big diesel engine to turn a generator that can power a whole building. That you can't do it with a lawnmower engine. It's not enough power. So let's take this one step at a time. The coil's area is L squared. So let's go with A. The area is 0.05 meters squared, which is, and again, those of y'all with your calculators, get them out and help me do the arithmetic. It says here 2.5 times 10 to the minus 3. Meters squared. Okay? The flux through it is B times A, or so that's 0.6 Tesla times 2.5 times 10 to the minus 3 square meters, or 1.50 times 10 to the minus 3 Webers. The initial phi. When they come up with 1.5 times 10 to the minus 3, what does this stand for? Lowercase w, lowercase b. Unit of magnetic flux, not magnetic field. Magnetic field, B sub naught, has units of Tesla or Gauss, where 1 Tesla is equal to 10,000 Gauss. What's the unit of flux, of magnetic flux? Not just like the little grill. You never cooked on a Weber grill? Well, Webers, or Webers, I don't really care how you pronounce it, as long as you recognize it. The difference between a Weber and a Tesla. What's the difference? It is. In fact, its units are Tesla meters squared. And be careful not to make the mistake of just out of habit or because it sounds right saying Teslas per meter squared. It's not. It's Tesla square meters. So that's your initial flux. 1.5 times 10 to the minus 3. After 0.1 seconds, the flux is 0. So delta phi delta t equals 1.50 times 10 to the minus 3 Webers minus 0 Webers. Initial flux and your final flux divided by 0.100 seconds, or actually I wrote those backwards. It should be final minus initial, but we've already looked at what the sign actually means, right? Can someone tell me what the sign in this would signify? No, the direction of the current or the polarity of the EMF. So basically, where do you put the red probe and where do you put the black probe? So somebody do the arithmetic? Who did it? And what did you get? Then try it again. I think you're off by 1 order of magnitude. Anybody else do it? .015, 1.5 times 10 to the minus 2, or 15 times 10 to the minus 3, however you write it. But it's Webers per second is the time rate of change of the magnetic flux. Now, what is the EMF induced in the total 100 loop coil during that 0.1 second interval? Minus N times d phi dt. Somebody? No. Minus N times minus 1.5. You're multiplying a negative times a negative. Again, I don't really care. But you're right. 1.5 volts, the unit of EMF. So, looking at the image on page 595, or this one up here, by Lenz's law, which way does the induced current have to flow? Now, the flux, it's got to go clockwise or counterclockwise. It can't go left or right. But by Lenz's law, as we pull this loop out of the magnetic field, what's happening to the flux? The magnetic field is fixed, it's constant, but the flux, the magnetic field per unit area contained in the loop, is decreasing. That means the current is going to flow in such a direction by Lenz's law as to add to the magnetic field to try and maintain the flux that it already had. That means it's going to produce a magnetic field into the board. And by Lenz's law, that's the direction the magnetic field has to go. By then, one of the right-hand rules of thumb, current here is going to flow up, so it's going to flow clockwise. All right. Now, did they give us the, yeah, they sure did. They said the resistance of this 100 loop coil, the total resistance is 100 ohms, which means that current that flows clockwise is going to be 1.5 volts divided by 100 ohms is, we're back to 15 milliamps. 1.5, or 15 times 10 to the minus 3. Is that right? Somebody do that arithmetic. Seriously, never trust me to do arithmetic in my head, okay? Just 15 milliamps. Good. All right. That's the voltage induced by this motion and the current induced by this motion. That means that you had to expend actual energy, and to do so, you had to exert an actual real force. So let's look at the energy that was dissipated in the coil. How would we calculate that? What is the energy dissipated in an electric circuit? Watts. E squared over R, I squared times R. Say what? I times V. In any case, that gives us watts. But watts is joules per second, right? So in order to get joules, you have to take watts times time. That's why the electric company bills you not for kilowatts, but for kilowatt hours. Well, in this case, what's the total watts produced here? Let's see, they go I squared R be I don't know. Let's see. Well, let somebody get out a calculator. You know, the current is 15 milliamps, so 0.015 squared times 100 ohms would be 22.5 milliwatts. Got it? Okay, but that many watts times 0.1 second gives us 2.25 times 10 to the minus 3 joules. Okay, that's the actual amount of energy expended pulling that wire out of that magnetic field and generating that much current and that much voltage. So, now just to drive the point home that this is all real, let's look at the amount of force that we had to exert in order to do it. So, force, what is the total work? Force times distance, right? So, force is equal to work divided by distance. We know the distance was 0.05 meters. How much work was done? .25 joules. Thank you. Actually, it's 2.25 millijoules, right? So that means the force exerted .0450 newtons. Or 45 millinewtons. Say again? Because watts is power. That's how much power was dissipated. But joules, energy, is watts times time. Power times time gives you energy. So, and that energy required that much force to actually pull that wire, that wire out of that magnetic field. And I'm quite certain that if we actually did this in lab, the force exerted on that wire by that magnetic field would be hardly noticeable, if at all. You probably have to. But it doesn't take much before these forces can become dramatically noticeable. And if you ever have a chance to use one of those meggers, make sure you're not standing anywhere near the business end when you do it, but turn that crank and feel how hard it is to turn those magnets inside all those coils of wire. And there's nothing there except induction opposing you. All right. Do we have any questions about any of this so far? We got 30 more minutes. So, we've seen that changing magnetic flux produces an electric field. How do we know that? Remember, we've talked about how much changing magnetic flux produces an EMF. But if there's an EMF, then the EMF is the potential gradient of an electric field. So if you're producing an EMF, that means you're actually setting up an E field, a vector field, inside those conductors, those wires. They relate this back to our previous section where we looked at the force exerted on a moving charge by a magnetic field, and they tell us that the E field is going to be equal to the velocity times the magnetic field. Now in our lab this week, we looked at those generators, those electric motors and the generators, at least to the extent that we could get them to work. What was one of the things we observed that was perplexing? Yeah, we couldn't make it spin the opposite direction. Why not? Exactly. 21.6, back EMF and counter torque eddy currents. Okay, I don't want to go into this in any great depth, but I do want to talk about the experiment that we did in lab to make sure that everybody's clear on what we observed. And it relates to Lenz's law. Anytime you move a wire in a magnetic field, you produce you induce a current in that wire. And when you produce a current in that wire, that current is going to flow in such a direction as to oppose the motion that caused it. So in that regard, the direction that you wind the coils on a motor, on a rotor or a stator, or when you start, if you ever get to where you're designing your own electric motor, you're going to find that the direction that you wind the coils matters as to whether it spins one way or the other. Okay. In the book, they talk about three things. They talk about AC generators. We saw the AC generator where the slip rings were split like so. Right? So the rotor, one side of the rotor was always connected to one coil, one polarity wire, and the other side was always connected to the other polarity of wire, of the power coming in to turn the motor. Or, I'm sorry, we're talking about generators. So the wire coming out of the one side of the loop was always coming out of one wire, and the other side of the loop was always coming out of the other side of the wire. So during half of the cycle, when the one loop is passing through the North Pole magnetic field and the other's passing through the South Pole magnetic field, it induces current in one direction. But in the second half of the cycle, the two swap and it produces current in the other direction. And you end up with an AC generator. So if you plot the current as a function of time, it literally makes a sine wave, assuming you can do it all consistently and steadily enough. And if you can't, then you get what's called dirty power. And if you ever find yourself working for some backwater electric co-op that's barely making enough money to keep their generators running, you're going to learn real quick what dirty power is like when you start losing light bulbs. I don't know how bad it is now with LEDs, but I know out where we live in Mason, and it's not because it's a backwater co-op, but just because we're so far out that the lines are so long and it goes through so many bad connections by the time it gets to our house that we couldn't keep lights in the porch lights on our front columns on our front door. They were constantly going out from dirty power. In the United States, how fast do those generators typically run? How fast do they turn? 60 hertz. That's the standard in the US. They turn 60 RPMs. Go to Europe and they turn them at 50 RPMs. I don't know about anywhere else in the world. But there's also, we looked at the other set of slip rings that were split vertically. So now, when the brush is passed from one to the other, the coil that was in the north, the positive coil was in the north magnetic field for half of the cycle. And when that coil gets over to the south pole of the magnetic field, it gets switched over to the negative polarity, to the negative side of the negative potential. Swapping back and forth. And then what we couldn't see because we couldn't get it to work steadily and consistently enough is that the current would do this. Now it's still changing from 0 to max back to 0, but it's all in one polarity. And so technically that would be a DC current. Well, by the standard definition. Another definition says that the AC, the frequency of the current, is the change in current with respect to time. You can see that this has some significant DI/dt, but it's still all in one polarity, so it's considered DC. DC generators tend to have multiple coils, so that while this coil is producing this current, the next coil is producing this current, and the next coil is producing this current. So the net current ends up looking more like this, which I think y'all will find in your other over in electronics courses, they're going to call that the ripple. Or is that what they call it over there still? That's what they called it when I was learning it. You stick big enough capacitor on it, you can filter out pretty much as much ripple as you want. I don't know that you can ever make it all absolutely go away, but you can certainly make it as arbitrarily small as you want. Just depends on how much capacitor you're willing to pay for. That's the two different kinds of generators, AC and DC. And one of you, I don't remember who, but one of you made an observation about this one while we were doing the lab. Who remembers that? You made the observation that there was a whole lot of sparking going on where the brushes met the slip rings. Why is that? Because everywhere it changes from one to the other, it has to cross an air gap. That is not an infinitesimally tiny contact point. So it has a definite width. So there's a point where it has to cross that air gap, and when it does, it arcs and it sparks and it makes ozone and all that stuff. That is why DC generators are generally not preferred. Who can tell me where DC generators were most commonly used up until, well, what in my memory is a few years ago, what in your memory was, like back in the old days, before y'all were born? Say again? Vehicles. Cars, trucks, they all use DC generators. In fact, they were called generators. And that's why the automotive industry got away from them. It's because of all the sparking and the arcing and the failures, because having those brushes cross that gap once every revolution or twice every revolution is that's some significant wear and tear on those brushes. It's literally scraping the inside surface of that brush off a little bit every time it turns. Became a very high failure point. Who can tell me what they introduced to make up for it, to replace it with? What do you put in your car now if you go to the parts store? Do you buy a generator or you buy a what? Okay, what's the difference between a generator and an alternator? Alternator is AC, that's correct. It means it uses this kind of commutator, a slip ring, so there's no gapping. What else is different about it? It has no permanent magnets. The rotor is an electromagnet. And these slip rings provide power from the battery to the rotor to create the magnetic field. And that magnetic field is then what rotates by the pulley of the drive belt. It rotates that electromagnet rotor inside a fixed stator of coils of wire. And those are the field. That's the field that then, that's where the current that generates comes out and goes and charges the battery and provides power for your vehicle to run. And I have no idea why they decided to make it that complicated. I know why they did it was to get rid of that, to eliminate that high fail point, to go to the more reliable, mechanically reliable configuration. But why they decided to go to the electromagnet core rotor and a fixed stator out, you'd have to ask somebody who actually did the engineering, because I've never analyzed it to try and figure it out. It's too easy to just undo the two bolts and plug in the new one, retighten the belt, and you're good to go. Huh? You're talking about the ones with the built-in regulators now? Oh, well, no, that's because now the automotive industry, they've gotten to where I swear I think they have contests each year to see who can put the most stuff in the least space. Well, there was my people I grew up with back in Louisiana, up in DeRidder, I used to ridicule them, saying that was their national pastime, was seeing who could fit the most engine in the least car. Yeah, they've gotten ridiculous. But believe it or not, when I was a teenager, I could change the alternator in my Dodge Aspen in the dark with 2 wrenches without ever even opening the hood. 2 wrenches in the dark, slide right behind the front driver's side wheel, knew right where the nuts and bolts were, reach up there, take out the old one, put in the new one. 5 minutes, I was done in the dark. I could do it blindfolded. So, on my old Dodge, tell you the story about that. On my old Dodge, I used to keep a spare starter and a spare alternator in the trunk. This was in a 76 Dodge Aspen. I did. As soon as one broke, I would change it, go to the parts store, swap out one, get a new one, stick it in the trunk for a spare. That's how often I changed them. And never at home. It was always on the side of the road somewhere. Then in 81, I bought my first sports car. I bought a Nissan 280ZX. I thought, oh man, that was a sports car. But I I went to the, I got the car. First thing I did was I called up the Nissan dealership, said, I want to buy an alternator for an alternator and a starter. They said, well, are you sure you need one? I said, well, no, not now, but I want to get one to have as a spare. They said, are you sure? They said, the alternator is $225, which was a lot more money then than it is now. And I was heartbroken. I thought for sure I had just made the worst mistake of my young life because I could not imagine paying. I'd buy an alternator for my old Dodge for $30. $225 for an alternator because it has the regulator built into it? What kind of con game is this? Well, needless to say, I didn't buy it. I figured, well, I'll wait till it breaks and I have no choice and I'll buy it. And I don't know, I drove that car for 10 years and never had to change it. The only thing I ever had to change in that Nissan was the oil. That was it. I changed the color once when I had it painted. But that was, that was eye-opening for me. I honestly, at that point, it just was, to me, I just thought that alternators and starters was just routine maintenance on keeping a car running. Yeah. I'd say again? That was about $2,000. New. Yeah. Yeah, mine was just two-tone. I went from solid silver to a silver body with blue hood. Don't anyone ever let him near one of my cars.
Going? No, it's transmission went out.
No joke. When I was a small child in the early 60s, like 62, 63, my father had an old Chevy pickup truck, an old step-side Chevy pickup truck. It wasn't old when he bought it. He bought it new, but he also bought it that shade of orange, just like OSU orange. Only it was the same color orange that they used for all the highway workers. The orange trucks that would stop and fix the road. Well, he took grief about that for all the years he had that truck until he finally decided one day he'd had enough of it and he was going to paint it red. And he did. With house paint and a brush. And bless his heart, he was my papa and I loved him dearly, but no. You and him, either one. Ain't either one of you allowed near my cars. And you think that 280ZX paint job was pricey. You should have priced a paint job for my Porsche. It was just a little 944, but it was still the fastest car I ever drove. No, it was water-cooled. It was a high-compression 4-cylinder. And on I-35 south of Dallas, I actually pegged the speedometer, which went up to 165 and then some. So, now my 280ZX, the fastest I ever got it up to was a little over 140. And yeah. What I found is that once you get to a certain point, because when I was doing 140 on the 280, I was on a 2-lane highway. Highway 27 between Sulphur and DeQuincy in Louisiana. And it was 2-lane blacktop, no shoulders, but I was getting irritated at the other drivers, like, come on, people, this is a highway, not a parking lot, no zipping. But there comes a point where it doesn't matter. You're going so much faster than everybody else, they may as well just be sitting still. So it doesn't matter whether they're oncoming or going the same direction. The relative speed doesn't matter. It's just like zip around them, through them, between them, you're gone. I didn't realize how fast I was going until I was come up on these big curves outside of DeQuincy, and I like, whoa, those went by fast. And that was the first time I realized how fast I'd been driving. So, a Ford pickup. I used to make fun of all the guys in Lake Charles driving their Ford, their big pickup trucks and the jacked up wheels and all the. It was like, you people, the closest you've ever been to off road was jumping the curb at Kroger's. Why are you buying this stuff? Why are you spending money on trucks? Buy cars, for crying out loud. Then I bought a ranch, and I actually had to haul hay and pull a trailer with cows in it, and so I had to buy a pickup. Yeah. 40 acres. Yeah. I'd love to have 100 acres. But, so that's back EMF and counter torque. What else do we have? I guess we're going to use transformers next week as our introduction into actually using inductance in circuits. And we'll look at how transformers step voltage up and down and mutual inductance. But in the meantime, does anyone have any questions for any homework assignments? Let me remind you that if you have late homework assignments, any labs you need to make up, you need to get it done between now and next Friday. Because after next Friday, thank you, there's no guarantees that it will get graded. After next Friday, I will still do what I can and work with you, but I'm going to have to prioritize the stuff that is due, and because I've got deadlines too. So I'm already giving up my whole spring break to get y'all caught up. So don't pile on is what I'm saying. You have a good weekend.